Hello, this is AMAT 104, lecture recording week 13.2. So today we're going to go over this problem called Monty Hall problem. Monty Hall problem. I briefly introduced this problem back when we were doing probability, and this is a very popular paradox regarding probability theory. And I did not really go over any solutions of this problem before. I'm sure some of you have thought about it. Some of you already know the answer. Some of you searched online. It's totally fine. So this is a very popular problem. And usually, if you are having in-class meetings, I would suggest this problem as a discussion problem because we often get a lot of different opinions on this. So I have introduced the problem, like what the problem is, how the problem goes, but I'm going to do it again. And today we're just going to spend the time just going over this problem. So it's also going to be a very short class. So suppose you are a contestant. I'm gonna write everything out for you. You're a contestant in a television game show, and you have to choose one of the three doors. To win either a fancy sports car or a goat, which means you lose. So behind three doors, let's say these are three doors, and there's the doorknobs, and behind one of these doors there is a fancy sports car, and the other two, it has a goat. So obviously winning a goat means you lose the game. So we don't know and behind which door the sports car is or the goat is. So suppose you chose door one. So in this scenario, it doesn't really matter if you chose door two, door three, doesn't matter. But let's assume without any loss of generality that you chose door one. So suppose you chose door one. So let's call this door number 1, 2, 3. Let's suppose that. And at this point, nothing has changed. And I assume you have already know that because we have one sports car out of 3 doors, you can simply say that your probability of winning the sports car, so the probability of winning the sports car is actually 1/3. And I'm sure by now everybody is aware of this. So now the host, in this case, the name is Monty Hall. That's why it's called the Monty Hall problem. So the host knows where the car is. So this is an important line. The host always knows. So the Monty, in this case, always knows where the sports car is. Opens door 3. and it reveals a goat. So to show a goat behind it. And he offers that you can switch the door. So, and offers you the option of switching. Obviously, this is door 2 because door 3 is revealed already. So we know that by now we have a goat is already chosen there. And in door 1, door 2, we still have no clue what's behind in the door, behind the door. So your current choice is number 1, and the host offers you an opportunity to change your mind and go to door 2. And here is the problem. Should you change door 2? So should you, the question here is, should you stick to your original choice? Or should you change? So should you change? Or doesn't matter even? Doesn't even make a difference if you choose door 2 or door 1. So this in the past even now, people argue a lot of different things, and this is a typical problem, and it's a very simple problem, but it's a very typical problem where the solution goes against your gut. Obviously, a lot of the times when you're in a game show, you really don't have time to think about the probability, mathematics behind it, so you usually just go with your gut. If you believe your gut, you would stick to your original choice and choose number 1. But if you want to take the chance, you probably go to door 2. But oftentimes there's usually no logic behind it. It's all about feelings. But the problem is, here we can look at the problem from more logical standpoint of view and take all the feelings and guts out of it. And let's look at it in a very dry mathematics point of view. So usually students would have a lot of different opinions, and a lot of you would think that it really doesn't make any sense because you're choosing between 2 doors, so it's 50-50. Or some students may think that some students still think that their gut is correct, but obviously that's at this point it's rubbish talk because it's not really, we're not talking about the feelings in these problems. So just to give you the answer is yes. You should switch. You should always switch. You should switch the door because it'll increase your chance. Of winning your car, obviously. So Why is that the case? Obviously, this doesn't really seem intuitive because your choice was 1/3. I mean, your probability initially was 1/3, and it was equally likely. No one door had greater probability than another. And now you're choosing between two doors. A lot of people would think that choosing door 1, door 2 doesn't make any difference. So let's break this down to 3 different cases. So there are 3 main cases in this scenario. So case 1. So suppose there was goat. And obviously we know there's a goat in the door 3 because that's the scenario where the Monty Hall opens door 3 and reveals a goat. So we know that there is a goat. And suppose there is a car in here. So in this case, if you stay, you lose. Obviously. And if you switch, you win. And this seems pretty intuitive, but this is obviously knowing what's behind it. So we're going to prove this by exhaustion. We're going to go through all the possible outcomes and show that, so we're going to exhaust all the different possible outcomes to see if it's correct or not. So this is the case 1. So we know that in this scenario, we're always assuming that you chose door 1 in the beginning and you're contemplating between door 1 and 2 at the end. So door 3 always has a goat, so, and that's a given. And case 2, is, let's say, so let's number the goats. So this is goat 1, this is goat number 2. Let's say that because 2 goats are different. So you have 2 different possibilities of getting goats. So suppose this was goat 1, car, goat 2. Then after you chose door number 1, the host will show you the goat number 2. And if you stay, you win the goat number 1, which means you lose. And if you switch, you win a car. In the second case, let's say in this case you have, we know there's a goat. And in this case, let's say this is a, excuse me, this is the goat number 1. And this is goat number 2. And this is a car. And this means that if you stay, you lose again. And if you switch, you win. In the third case, so you know there is a goat in the third one still. And let's say this is a car here, and there is goat 1, goat 2. So in this case, goat number 1 and 2, the places do not really matter because you're not the one really initially chose the goat. So in this case, if you stay, you win. And if you switch, you lose. So as you can see that in all three of the cases, when you stayed, you lost 2 out of 3. And if you switched, you won 2 out of 3. So we can see that switching, you have a greater chance. Obviously, this may not be the best explanation. So I'm going to supplement it with some other explanations. So if you look at the design of the game, so behind the design of the game, you can see that from these 3 cases as well, because the host will reveal the goat regardless, you know that if you initially chose the goat, there's going to be the car in the other door regardless, and that's a given. Similarly, if you initially chose the car, obviously you don't know what you chose, but looking at what's happening behind the doors, if you chose the car, when the host reveals the goat in door 3, you know that if you switch, you're going to get the goat. Does that make sense? So this actually implies that if you switch, you're always going to get a different choice from your initial choice. So if the problem is designed that if you choose, let's say if you chose a goat in the beginning, then you will always have a car. When you switch. And vice versa. So if you chose a car in the beginning, you'll always have a goat when you switch. You can also do this by exhaustion. If you had a goat and you had a car and you had a goat, so door 3 is always a goat because host is going to open it. So you chose door 1, and obviously you don't know what's behind it, but let's assume there's a goat. Then because door 3 is always the goat, the door that the host is revealing is always a goat. When you switch, it's always going to be the car in the second. Similarly, if you chose the initial door and suppose there was a car, obviously you don't know there was a car or not, but because the host is revealing door 3, which always has a goat, if you switch, you're guaranteed to get a goat. So the problem is designed that if you switch, you're always going to get a different choice. You're always going to win something different than your initial choice. So if you switch, you will always, actually, let's say you are guaranteed to get something different from your initial choice. Does that make sense? So this is because, so it doesn't matter if you chose door 2, door 3, it doesn't matter. So just by knowing the fact that the host will open the one with the goat, eliminating the other choice of goat, if you chose the car in the beginning, you're always going to end up with the goat if you switch. Similarly, if you first chose the goat, you're always going to end up with a car if you switch. So this actually is very important to know, because this comes to this basically comes down to this. So the probability of winning. So probability of winning after switch is actually exactly the same as probability of losing with your initial choice. Meaning that probability of choosing goats or choosing a goat in your initial choice is exactly the same as the probability of winning if you switch. Similarly, what this implies is it's equivalent to saying the probability of losing after switch is exactly the same as probability of winning with your initial choice. So we can see that the probability of losing in your initial choice, meaning the probability of choosing a goat out of 3 doors, in this case it's 2/3. Because we have 3 doors, we know there are 2 goats behind the doors, and there is 1 car. So if the probability of losing with your initial choice is 2/3, and it's exactly the same as probability of winning after choice, after switching, that implies that you will win 2 out of 3 times, or with the 2/3 of probabilities if you choose to switch. In other words, if you probability of winning with your initial choice is 1/3, because that's the probability of winning a car out of 3 doors, and it's exactly the same as probability of losing after switching, so which in this case is 1/3. So as you can see, we know that the probability of winning after switch is 2/3, and not switching is 1/3. And we can probably see that your chances, your probability of winning has increased by switching to 2/3 from 1/3. So yes, with this explanation as well, you're always better off by switching your choice in the end. So maybe the first explanation was better, maybe the second explanation was better. People understand things, perceive things differently. So I'm going to give one last explanation. So this is actually a less mathematical explanation, but it's more like an example-based explanation. So explanation 3. So suppose that there is a deck of cards. So let's say, so this is a similar example. But more extreme. So suppose you have a deck of cards. And this means that you have 52 cards. And let's say you're trying to find and suppose you are to find ace spade. Obviously, so your probability of winning is 1 out of 52. Obviously, all the cards are none of the cards are revealed, so they're all face down. So without knowing what's behind it, you are to choose one of the cards. And obviously, by this time, you have 1 out of 52 probability of choosing the ace spade. Obviously, that's not very likely. And suppose the host reveals, let's say, 50 cards that are not ace spade, leaving 2 cards unrevealed. And these 2 cards are your first choice and one other card. So you're given 52 different choices and you have to choose one to find this one specific card. So you chose one, and then the host decides to reveal 50 of the ones that you didn't choose, leaving 2 cards that's unrevealed. And none of the cards that the host revealed is the one that you're trying to find. And in this case, would you switch or not? So would you or should you switch? So here, let's think about the gut, the gut you are trying to explain. So in this case, would you trust your gut in the beginning with the 52 cards that are unrevealed and you chose one? Would you choose that gut, or would you choose the other card that the host just mysteriously just left unrevealed? What do you think has more probable? Which card do you think is more probable to be the one that you're trying to find? So obviously, it may actually not be obvious to you, but to me at least, it's very obvious that odds are against your favor if you didn't choose, if you didn't choose to switch. If you switch, whatever that mysterious card that host left with you is, I have a feeling that that's going to be the right one. Obviously, this is not a mathematical explanation, but this is an extreme explanation where you are given X amount of choices and you have to choose one exact correct thing. But at the end, you are left with one or the other, your choice between this one or the one that you didn't choose. So I'm not sure if this is a good enough explanation either, but this is an extreme example where people can actually see. And in this example with the 52 cards, people's gut will actually, their feelings and like their instinct will actually drive them into the correct direction. instead of when you're only given 3, because 1/3 is still a huge probability. So I gave 3 different type of explanations for this problem just then. So remember, when you're given this problem, you always have to you always have to choose a switch, and then you'll have a better chance of winning. Okay, so that's all for today, and thank you for joining the class, and I hope you have a great rest of the day.